Okay, in 17.8, let's look at number 2. And it asks us to use Stokes' theorem to evaluate the curl F dotted with ds. So we have above the plane z equal 5, so z is greater than or equal to 5. The surface is z equal 9 minus x squared minus y squared. So where they intersect, x squared plus y squared is 4. And we need to go counterclockwise around this boundary. So what we're doing first is finding the boundary. So that's where the plane intersects that surface. That's a circle, so we're going to use, we're going to parameterize it. We're going to say r is 2 cosine t, 2 sine t, z is 5. So this is x, y, z, and this is r of t. Now make sure you have it going counterclockwise. So we'll test it. At 0, this is going to be the point 2, 0, 5. At pi over 2, so basically that's just 2, 0. Pi over 2 will be 0, 2, 5, so it'll be at 0, 2. So we are going counterclockwise, so make sure you always parameterize the curve right. R prime of t the derivative is this, and then f of r of t is going to be we're plugging r into f. So the integral around c f r of t dotted with r prime of t is going to be 0 to 2 pi. We're going to take f and dot it with r prime, and that gives us negative 20 sine squared t plus 20 cosine squared t is 0. That's cosine squared minus sine squared is the double angle formula for cosine. So when we integrate that, we get minus 20 sine 2t over 2, 0 to 2 pi, and that gives us 0. Okay. You want the part of the cone between y equals 0 and y equals 3. So if you take those values and plug them in, we have 9 equal x squared plus z squared, and y is equal to 3. We have to parameterize that curve. What we're doing is getting the intersection between that and that for the boundary of the surface. You intersect those. So we want r of t. If we did 3 cosine t y is 3, z is 3 sine t. Then at 0, we're going to get 3, 3, 0, which basically is 3, 0. On the xz axis, which is right here. And then if we do pi over 2, we're getting 0, 3, 3. So 0, 3, we're going that way. And that's clockwise, so we can't use that. So let's just switch them around. We'll do 3 sine t, 3, 3 cosine t. And at 0 here, we're going to get 0, 3, 3. So we get 0, 3 first. And then at pi over 2, we're going to get 3, 3, 0. So 3, 0 is going counterclockwise. So this will go counterclockwise. We always have to make sure we are traveling around the curve in a counterclockwise direction. Okay, so r prime of t and f is going to be taking x, y, and z and plugging it in. Okay, and I want to integrate that from 0 to 2 pi. I'm going to go to Maple and do that. Excuse me. Okay, so I'm going to type in, integrate 2187 times sine of t times cosine of t squared minus 81 times sine of t squared times cosine t. And I want t to go from 0 to 2 times pi. And we get that. So, and if you want to evaluate it, that's the exact answer. If you want to get the approximate answer, we get 1,717. Okay, so that takes care of the integration. Okay, let's look at number 8. I'm going to do the curl first. And we have plane 2x plus y plus 2z equal 2 in the first octant. That gives us z equals 1 minus x minus a half y. Let's see, if we draw that, we get point 0, 0, 1, 1, 0, 0, 0, 2, 0. That's the plane cutting across the first octant. Here is our D. So I'm going from 1 to 2. And the equation of that curve you can find out is y equal 2 minus 2x, because we've done that before. So when I integrate this, I'm going to go from 0 to 2 minus 2x minus p. These where p, q, and r are the components of the curl of f. Okay, so the curl of f, that's why we had to find it, was 0, 0, e to the x. That was up here. So I have 0 times, this is g, so g with respect to x is negative 1, q is 0, this is minus a half, and r was e to the x, or, yeah, dy dx, and x just goes from 0 to 1. So integrating that with respect to y of e of xy, 0 to 2 minus 2x, is e to the x times 2 minus 2x. And then I integrate with that with respect to x. I'm going to use the, well, we can do parts. That's the integral of that. So integrating the first one, I get 2 e to the x minus, the next one is 2x e to the x plus, because there's two negatives, 2 e to the x, that's from the parts, and then I'm going from 0 to 1. So, excuse me, that's going to give me 2e minus 2e plus 2e minus 2 plus 0 minus 2, so that's going to give me 2e minus 4. Okay, let's look at 14. Okay, we run across that same plane, pretty much. This is 2, this is 2, this is 1. That's the equation y equal 2 minus 2x. First off, we're going to parameterize these boundaries. Okay, so with A, that's the line segment from here to here, so A is going to be, R is 1 minus t times the starting point, which is 0, 0, 2, minus t, or plus t, times the end point, which is 0, 0, 2. Sorry, that's not the start point. The start point is 0, 2, 0. So that's going to be 0, 2 minus 2t, and 2t. C is the line segment has to go that way from 1, 0, 0. Make sure you get your directions right. And C goes from okay. So once you got that, you got your boundary curve, and you parameterized it. So we're going to do f dotted with dr, which is f evaluated r of t times r prime of t. Okay, so the first curve, it's going to be f is just y. Well, f is x. So it's x. We're doing curve A, and curve x is 0. Let's see, r prime is 0 minus 2, 2. So 0 dot with 0 plus for A, f of r is 0, y, x, y, z. And I'm going to dot that with this right here. So I'm going to dot these two. And I get minus 4 plus 4t. Okay, for B, f of r is x, just 1 minus t, y, and multiply them all together, x, y, z, and r prime is minus 1, 2, 0. So that's for curve B. So when you dot those, you're going to get minus 1 plus t plus 4t. And then for C, I have f of r is x, y, x, y, z, and r prime is 1, 0, 1 minus, just minus 2. I dot those, I just get t. So if I add all those together, I get 10t minus 5, and I'm going to integrate that from 0 to 1, because when I parameterize the line segment, t is always be between 0 and 1. Okay, I get 0 if I do it that way. Now the other way, I should get 0 also, because they're the same. Here I find the curl of f. Partial with respect to x. So I'm going to do minus p times z is the plane. So dz dx is minus 2 plus yz, that's minus q times dz dy plus r, 0, dA. And then on the y, I'm going from 0 to 2 minus 2x. And x goes from 0 to 1. I multiply this out. I substitute this in for z. So I get 2x minus y times 2 minus 2x minus y. I factored out the minus x and the minus y, or the plus 2x minus y. And when I integrate that, with respect to y, I get just a lot of arithmetic. Integrate that with respect to x. And I get 0. So that shows that those two formulas are comparable. Okay, there you have it.